Monochromatic light of frequency 6 into 10 power 14 Hz is produced by a laser. The power emitted is 2 into 10 power minus 3 watt. What is the energy of the photon in the light beam, and how many photons per second on an average are emitted by the source? Let's solve it. So we know that energy of photon is given by h nu. We are given frequency, and h we know 6.6 into 10 to the power minus 34, and frequency is 6 into 10 power 14. So if we evaluate, we will get 3.98 times 10 to the power minus 90 joule. So this is energy of one photon. And here power is given, and we have to find out number of photons per second. So number of photons per second can be given by energy total per second, which is power, divided by energy per photon, means energy of one photon, energy per photon. So in our question, energy per second is power, that is given 2 into 10 to the power minus 3 watt, and energy per photon we have got as 3.98 into 10 to the power minus 19. So if we simplify, we will get 5 into 10 to the power 15 photons per second. Now let's go to next question. The work function of caesium is 2.14 electron volt. What is threshold frequency and what is the wavelength if the stopping potential is 0.6 volt? So here work function W0 is 2.14 electron volt. That is h nu 0, which is work function, and 2.14 into 1.6 into 10 to the power minus 19. So nu 0 will be equal to 2.14 into 1.6 into 10 to the power minus 19 divided by value of h 6.6 into 10 to the power minus 34. So if we evaluate it, it will become 5.16 into 10 to the power 14 Hertz. Now our second task is to find the wavelength. So we know, according to Einstein photoelectric equation, h nu equal to h nu 0 plus ev 0. So here we can write this term as hc upon lambda equal to h nu 0 plus this e plus ev 0, and we have to find out lambda. So for that, what we write, lambda equal to, we take lambda to RHS, and then it will become hc divided by h nu 0 plus ev 0. Now we can put the values. So h is 6.6 into 10 to the power minus 34 times c is 3 into 10 power 8 divided by h nu 0. H nu 0 is this much energy, that is 2.14 into 1.6 into 10 to the power minus 19 plus EV0. EV0 means electronic charge, 1.6 into 10 power minus 19 into voltage 0.6. Now we can simplify it. So we will get lambda equals 454 into 10 to the power minus 9 meter, or 454 nanometer. Now let's go to next question. The wavelength of light in the visible region is about 390 nanometer. So here lambda 1 is 390 into 10 to the power minus 9 meter, and lambda 2 is given as 760 into 10 to the power minus 9 meter. Now we have to find out energy E equal to hc upon lambda. So E1 will be hc upon lambda 1. We put the values. So E1 will be equal to h 6.6 into 10 to the power minus 34 times 3 into 10 to the power 8 divided by lambda 1 is 390 into 10 to the power minus 9. Now we can evaluate it. So it will become 5.10 into 10 to the power minus 19 joule. This can be converted into electron volt by dividing electronic charge. So if we divided 5.1 into 10 power minus 19 divided by 1.6 into 10 to the power minus 19, so we will get it around 3.19 electron volt. Similarly, for second wavelength, E2 we can evaluate, so that will be same, except here in place of 390 to 10 power minus 9 we will write 760. So 76, sorry, so it will become 6.6 into 10 to the power minus 34 times 3 into 10 to the power 8 divided by 760 multiplied by 10 to the power minus 9, which will become 2.62 into 10 to the power minus 19. If we convert it into electron volt, so 2.62 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19. So that will come out to be 1.64 electron volt. So this is our answer. Now let's go to next question. Next question is, what is the de Broglie wavelength associated with an electron moving with a speed of 5.4 into 10 power 6 meter per second and a ball of mass 150 gram traveling at a speed of 30 meter per second. So let's evaluate it. So we can find the momentum. Momentum of electron P equal to mv. We put the value 9.1 into 10 to the power minus 31 into velocity is 5.4 into 10 to the power 6. So this is momentum that comes out to be 4.92 times 10 to the power minus 24 kg meter per second. We have got momentum and we know that de Broglie wavelength is given by lambda equal to h upon p. So 6.6 into 10 to the power minus 34 divided by value of momentum 4.92 into 10 to the power minus 24. So if we evaluate it, it will come out to be around 0.135 meter. Now consider the case of ball. So here its momentum, suppose it is F1 equal to momentum is, say this time it is P2. So we take P2 equal to mass is 0.150 kg times velocity 30 kg meter per second. We have got momentum. Now wavelength for this, suppose this is lambda 2 equal to h upon P2. So h is 6.6 into 10 to the power minus 34 divided by momentum is this much, 0.15 into 30. So if we simplify it, so we will get lambda 2 equal to 1.47 into 10 to the power minus 34 meters. So the de Broglie wavelength of electron is comparable with X-rays wavelength. However, for the ball, it is about 10 power minus 19 times the size of the photon, quite beyond experimental measurement. So we can't measure the wavelength of this, but we can easily measure the wavelength of electron. Thank you for watching.